All right, let's begin with a few basic examples of inverses, and in fact, for now we will just call these inverse relations. What a relation is we still have like a domain and range, right? We might still have x and y, but we don't know for sure if it's a function or not. It may or may not be. All right. So an inverse, all an inverse really means is to switch the x with the y, or the domain and the range. Okay, so if we have some relation that tells us, if x is 7, then y is 8, well, the inverse relation is simply 8, 7 then. All right, and 8, negative 2, and negative 4, 3, and then negative 8, 8. All we do is we change the x and the y. We change the domain and the range. If we had menu items at McDonald's, I'll squeeze in another example without an x and a y here. So we had a bunch of menu items, right? Whatever they are, 1, 2, 3, and then the relation is the price. That would be, you go to McDonald's and you order a cheeseburger, right? They tell you whatever price it is. Well, instead, imagine going to McDonald's and you have a fixed price. I only have $3 on me. What can I buy, right? I might look at this problem differently. I might look at the price and see which items I could afford. It's the inverse. It starts out fairly easy, and we will need this for a few things as we move forward. So what if we have an equation like this second example here? Again, we switch the x and the y, so now it's y to the third x equals negative 5. With functions, we typically solve for y. Sometimes it's just not possible, and maybe it isn't even a function. Maybe it's a relation, right? Think of like a circle. I could add another example here. We had circles x squared plus y squared equals 9, circle with radius 3, right? Well, if I change the x and the y in this example, it does nothing. But this relation was not a function, right? Because I knew it was a circle with radius 3, and it didn't pass the vertical line test. So it wasn't a function. You might start seeing certain restrictions to make this a function, though. Maybe it restricts the domain if this same problem said, x and y are both greater or equal to 0, or even just y is greater or equal to 0. That would actually work as well. But either way, if they're both greater or equal to 0, now we're only talking over here, right? And we would have a function and whatnot. But point is, you're going to see certain problems pop up in different ways when we begin to look at inverses. All right, the last example I wanted to share as far as inverses go is we've kind of been looking at things a few ways. Numerically with a table, algebraically, right, analytically, which is the most common, especially for college algebra, but also graphically. It's important, to keep a visual understanding of what's going on. What are you doing? So what is an inverse looking like on a graph if we change the x and the y? So I have some points here. I purposely didn't really draw on a grid or get it precise. More so I want to demonstrate something. So let's say like we are here, I don't know, maybe negative 2, right? Negative 2 up to, something like that. Pretend. But point is, if we change the x and the y, negative 2, 2, we're now at 2, negative 2. So now I'd actually be 2, negative 2. I'm down here. Well, let's take a look at a couple more. So let's say at 1, again, rough approximation, I may be up here at about 5. Right? And if I change that 1, 5, if I change the x and the y, if I'm doing the inverse, I'd have 5, 1. Okay. Oh, I'm sorry, negative 1, 5. I knew something was wrong when I said that out loud. Negative 1, 5. I now have 5, negative 1. So now I'm, somewhere over here. If I look at a point over here, I don't know, negative 5, 1. Right now I'm at 1, negative 5. So I'm somewhere down here. But point is, you could kind of see what's happening, right? As this is going up, instead of going up, we interchange x and y. We're actually approaching infinity to the right, where we were approaching infinity, moving upwards, right? And same thing here, approaching negative infinity. Well, now as we move left here, we'd go to negative infinity. This is important as we move forward. An inverse will always reflect about this line y equals x, right? This diagonal line has slope of 1, y-intercept is 0, it's y equals x. And notice it's a mirror image. Like if I folded that paper, these two, of course I'm not 100% accurate in my freehand, but those two graphs will line up on each other. It's the line of symmetry. Okay. One last thing I'm going to throw in here is we have what is called a one-to-one function. One-to-one function. And again, just the basics. So first off, note I said function. So if we're looking at a graph, it has to pass a vertical line test. Right, it means that if we looked at that first set of coordinates over there, 7, negative, or 7, 8, somewhere right there, negative 2, 8, I'm just free sketching 3, negative 4, somewhere down here, 8, negative 8, down here. Right, we had a function because one way we could think of it, it does pass vertical line test, but I really don't want to graph everything. But also each input has one output. So that has to be true, right? Each input only goes to one output. So the menu item for McDonald's, right? Each input I said should only have one price. That's a function. Now one-to-one, let me read this book definition. If different inputs have different outputs, then the function is one-to-one. If A does not equal B, then f of A does not equal f of B. Like, what the heck does that saying? There are other definitions as well. But if these are two x's, so if the x's are different, then the y's have to be non-equal as well. But notice in this first example, I have, so 7 does not equal negative 2, right? I have two x's that are not equal. But it implies that the y's, the f of A was 7, right? 7 went to 8 is not equal to, I also have 8, but that's not true. So what does that mean? That means this is not one-to-one. What does this look like on a graph? It would actually pass to be one-to-one. It would actually pass a horizontal line test. Okay, that's kind of the easier way to think of it in a graph. So horizontally, I'll just do a highlighter. These two hit the same horizontal line, right? That would not be one-to-one. Even though this first thing was a function, it is not one-to-one. Let's look at the graph that we have here. First off, it passes the vertical line test, right? No matter where I draw a line, it only crosses once. Well, if I draw it horizontally, this graph would only ever cross once as well. So therefore, it is a one-to-one function. Okay, it is a function, and it is one-to-one. We'll look at that more in a bit, but here are the basics of what we need for an inverse.